rings of electrons. So how do different levels like correlate to the actual physical structure of an atom?
So that's the thing, yeah, it's not a hard set ring like Saturn, right? But it is a space in which they dwell.
Okay, so it's like a 3D volume.
Yeah. Yep, think volume, think level. So it's not just like a ring, but there's this first energy level, second energy level. I also think of like, it's just like, breaking down like the core of something. So yeah.
Russian nesting dolls.
Say that again.
Are they separated by nodes or whatever that was in the nodes?
Yes. So there's areas where they overlap, and those are the different nodes.
Okay.
So yeah. Okay, so then, now this is where it gets very subatomic for us, okay? Within each energy level, there are what we call subshells. So this model doesn't show those. All this model shows is energy levels. So you have to pretend and imagine with me here, inside this energy level, if we could see deeper, we would see subshells. Okay? So the rooms of our hotel, where'd my marker go that I wanted? This one. Okay, so on each floor, there are rooms. The rooms are the subshells. Okay, so in an actual atom, on the first energy level, how many subshells are there?
Two.
One subshell, because there's only one type of room, but how many electrons can be there?
Oh, two.
Two.
Okay.
Okay, now pretend here if we could see it on this second energy level, how many subshells are there? Two. Right, there's this type of subshell, and there's that type of subshell. Okay, subshells have been designated by different letters. All of the subshells that are this size, we call an S subshell. So this right here would be called the 1S subshell because it's on the first floor and it's an S subshell. This would be called the 2S, 3S, 4S, so on and so forth. These type of subshells are called p orbitals. These ones are called D, and those ones are called F. So they've just given a letter to the type of subshell that it is. Notice what's the same about them is all p orbitals have 3 bunk beds, right? So all p's are the same in size. All the s's are same in size. And they're also, if we think in 3D space, they're also the same shape.
Okay.
Okay? All right, so we have rooms, we have subshells. Now, inside our rooms, what do we have? Good. We have our bunk beds. These bunk beds, so once again, we're getting crazy quantum subatomic here.
Oh dear.
Inside those subshells that we can't see in this model, there are individual orbitals. Okay, inside these subshells are individual orbitals, and those are like the bunk beds in the room. Then, pretty much after that, on each bunk bed is an electron. So then we can finally find where an exact electron will be. Is we can take it down from energy level to the sublevel to the orbital to are they on the top or the bottom of the bunk. That corresponds, I guess I wrote my analogy weird. So we go to bunk beds, we then go to top or bottom of the bunk. This is equivalent to the spin of our electron. That when electrons are in a shared orbital, one must spin up and one must spin down. That's why, once again, it's a bunk bed. So one electron sleeps on the top, one electron sleeps on the bottom. Yeah, Peyton.
So what does like this bunk bed, like what would it look like?
That's hard. I'll show you a picture here in a second.
Is it going to be like a 3D?
Yeah, because I can't describe it.
Yeah, I don't think you'd be able to.
But I'll show you a picture here in a second. That should hopefully help. And I think someone asked that last time too. I don't remember if it was in this class or not, but about like how do I look at this thing. So, okay, any general questions right now connecting this to what's going on inside a real atom? See the basic idea of what we're trying to piece together? Okay, so we're going to skip this table.
Okay.
Yep, we're going to skip this table. Don't worry about that table. Don't tell B6. I just put that on flip. Okay, so come now. We now understand the structure of our hotel. What we now need to understand is there are rules to the hotel. So when electrons come to check into the hotel, so let's say we're neon, and there's 10 electrons coming to the neon hotel, and we need to figure out, okay, which rooms, which bunks, where are we going to put these electrons? There are rules in which have to be followed. Okay? Rule number 1 is known as the Pauli exclusion principle. This rule is the one that tells us that electrons must have a unique set of 4 quantum numbers. Those things I just erased, those are the quantum numbers if you get really specific. That there's a quantum number for energy level, there's a quantum number for subshell, there's a quantum number for orbitals, and there's a quantum number for spin. I have yet to see an AP question that actually asks you about quantum numbers. All the questions are about writing a configuration. So that's kind of why I'm keeping the quantum number stuff off to the side to not get confused on something that I feel like you can understand it without fully understanding quantum numbers. Okay? If you want to have a talk about quantum numbers later, let me know.
I do.
Question?
No, no.
Oh, just stretching. Okay, so with Pauli's rule, write down this example in your notes. So let's say we're looking at an s orbital. Okay, the way we draw orbitals is actually as boxes. Okay, so if I draw one box like this, how do I know it's one box if it's S?
Because S always has one box.
Good, because S is one bunk bed and like the bunk beds are the boxes. Okay? Now underneath it I'm going to label which one it is. So it's the 1S. It could be the 2S or 3S or 4S. That doesn't really matter.
How do you know whether it's 1S or 2S or 3S or 4S?
Well, we know we always start at 1, so that's where I'm starting. But we'll get to
Okay.
that here in a second.
All right.
Okay? Now, the thing about Pauli's rule is when you have 2 electrons in the same orbital, one must spin up, and so we do an up half arrow. When we draw electrons, you do them as these half arrows. If that really bothers you, I really don't care if it's a full arrow, but that is the way it's typically done. And then we have one arrow going down. You will never ever have it where both of the electrons are going up. That breaks Pauli's rule.
Well, and the arrows are both facing the same direction, and that's weird.
I guess that too, right? But Pauli's rule tells us that no 2 electrons can both be spinning the same way. Yeah.
Why is that?
Think of electrons, right? What are electrons charge?
Negative.
Negative, right? So 2 negative things in the same orbital are going to repel each other and spin opposite directions, right? Because they're magnetic, their electric fields will force them to go the opposite ways. So, question on Pauli's rule? Okay, now let me back up real quick just to visualize. So the thing about electrons, everyone, is you got to recognize they're doing a lot inside an atom, right? They are orbiting the nucleus in 3D space, so it's not even just like this, but it's in like 3D space.
Are they
And then
really
at the same
orbiting?
time, they themselves are spinning.
What in the world?
So I can't do that with my hand.
So it's like
But
planets.
pretend my hand is rotating in circles as it orbits. That's what we mean by spin.
So it's
So like,
a planet
yeah.
spinning.
Similar to how the Earth spins. Wait, what did I just say?
The Earth
The
spins.
Earth would spin while it
While it's orbiting the sun. Thank you. Okay,
Why does it? What's making it spin?
the electrons?
Yeah.
The negative charges of all of them. just because the negative charge of 1
Repels. and
repels and
they
just dip.
So do they change spins?
They could, but they're always going to be opposite.
Yeah.
Yeah. Yeah. All right, rule number 2, everyone. I'm going to erase this.
You do it real slow. I'm scared at it.
Okay, so rule number 2. This is the rule that tells us the order in which the hotel rooms have to be filled. So there's a very particular order that is normally always followed. We'll talk about the exceptions later because they're always there, right? But the nice thing about this pattern, okay, the pattern of how they get filled go as such. You always go 1S, 2S, 2P, 3S, 3P, 4S, 3D, 4P. Everyone got this?
Yeah, sure, totally. Yep, memorized it.
So this is a map to the order. Okay, so I want you to pull out your orange periodic table and we're going to label some things on there.
I love it.
I was gonna say that's the shape of the computer.
Yeah. And you can just outline it too, but yeah. Okay, so what I want you to do on your orange periodic table, everybody. Now, when we use the periodic table as our map for the hotel, first off you need to recognize there's designated sections. Okay? This section, so what I want you to do is either color or outline these 2 columns. The ones in pink up here, this is the S section. Okay? So draw a box around these 2. Now what do you notice is a little weird about this periodic table?
Helium's on that side.
Good. So Declan and Max notice, where does helium fit with our sections? In the S, right? So make sure you recognize that.
Helium, why do you gotta always break this?
Okay? It's one or the other, right? Hydrogen goes that way, helium comes back. Okay, so outline that. This middle section is the D section. Okay, this is the P, and then down here is the F.
What about the 2 yellow?
Good. So this one's a little weird, but you'll note. Look on yours, Peyton. Where's LU and LR on yours?
Oh, it's actually.
It's where it should be, and that's why they are colored yellow because they belong in the D. For whatever reason, this one just cut them out to make it fit. But notice the coloring of it. Okay, so outline the S, the P, the D, and the F. You either color them or just recognize them as different sections.
Wait, this is that.
Yeah.
You need any?
No, that's D.
But this is
What are they?
Oh, no. This is the D. That's it.
Okay,
so pull out, right, highlight or whatever, those, the S, the P, the D, and the F. Yeah, so P is the far section.
I'm gonna see.
And then we'll look at how we read our map.
Maybe it magically appeared here.
that would be very nice. Will be orange.
Okay, so if you're a perfectionist, speed it up a little bit. We don't have all day to color boxes.
I do have
You might have all day, but I don't have all day.
that is true.
I don't either.
Because I want to teach you this because there's a test on it.
They're going to be looking at this for the rest of the year. They need it perfect.
Okay, so as you color, okay, I'm gonna give you, can we be done in like 1 more minute?
Yes, very cool.
Okay, one more minute and then finish up your coloring, or at least outline it, right? You can fill it in later if you want. Question? Great question. So if you go to your I Can paper, I don't know where mine went. I think there are 2 questions about configurations and 1 question about PES. So 3. Yeah, they're just part of it. Yeah.
Off bound.
Chaotic, my periodic table of elements gives.
A roofa.
So take a look at your map here, everybody. So the way that you read the map is you start at the top, you read left to right, and then you go down just like you would read a book. Okay, so the order that the hotel fills up, and we're going to do it in a little like chant together. Okay, so the first one that gets filled is the 1S room. Notice, because that's what's at the top. Now you read across, there's nothing else there. So then the next room that gets filled would be 2S. Okay, after the 2S room gets filled, then we come to the 2P. After the 2P gets filled, we'd come to the 3S. Then we'd come to the 3P. Okay, you ready? So we're going to like say this all together so I can see if we got the right idea. So I'm going to point and you guys are going to say which room we're at. Okay, ready? So we go.
1S, 2S, 2P, 3S, 3P, 4S.
Okay, very good. Now pause for a second. So, what happens here, because remember that these things are energy levels, okay? The 3rd and 4th energy level
Oh no.
and other energy levels have overlapping regions. So even though it's part of the 4th, there's levels of the 3rd that are higher in energy because of the overlap. So what we get right here is that it goes 4S, but this first row of D is part of the 3rd. So we call it 3D. So you might want to write that like on your periodic table. Just remind yourself like, hey, this starts at 3D. But the nice thing is notice, after that it just goes numerically, right? So if this is 3D, then the row below it would be 4D, 5D, 6D. Now we also have some crazy overlap regions when we fall into the F block. Yes, so first off, you need to visualize the periodic table like this when you're doing configurations. This is the real way in which the periodic table looks when you put it in number order. That whole F block, so watch again, ready? The F block should fit, because look, 55, 56, 57. It should fit right there. Normally, you see it like this.
And why is it?
Because it fits on a page better.
To be honest, yeah, the only answer I can really come up with is that it fits on a piece of paper. I have yet to actually really know.
I want to look it up.
Yeah, let me know if you find anything new. Okay, but when we go in order, we need to go in this order because it goes in numerical order. Okay? Now, there is a nice pattern, okay? So we said, so the S's start at 1, the P's start at 2, the D starts with 3, and the F starts with 4. So if you get all the way down to this section of the periodic table, you're going to go 6S, 4F,
No, no.
5D,
Ew.
and 6P.
Oh gosh.
Okay, but literally, guys, like, this shows you all of it. If you can just see how it fits together, right? It's not like you're memorizing the order because you'll always have a periodic table in front of you. Okay?
It looks like a wrench.
Okay, that's the basics of off-Bos rule.
Yeah.
Is that you have to go in that order every single time. Okay, we'll come back and do an example, but let's talk about the last rule real quick. So the last rule that we have to follow is called Hund's rule. The thing about Hund's rule is this, is the electrons, when they are in separate orbitals, must have parallel spins. And if they don't have to pair up, they don't pair up. Okay? It's just like any human being. If there's two bunk beds and there's two of you, you're each going to take your own bunk bed. Most of the time, right? Electrons do the same. So, let's say, okay, so let's just say I'm going to look at a P subshell. So how many bunk beds are in a P room? 3. So when we draw a P, you draw 3 boxes, but they need to be connected. Because it's one room, but 3 bunk beds. And I'm going to label this, let's just say it's 2P. But it could be 3P, 4P, whatever. If 4 electrons are being put into this room, the way you have to do it according to Hund's rule is they each take their own first, and then they pair up. And they each take the same spin. Now, it doesn't matter if they all go up or they all go down. They just have to be the same. So what I always do is I always say up, up, up. And then, now that one's going to have to share because there's 4 of them.
Or they could sleep on the ground.
But what they wouldn't do is you wouldn't have a case like this. That would violate Hund's rule to have an empty orbital when things are sharing. Okay, so they don't do this. And they also wouldn't do this, where one's up and the other one is down. That's what it means by parallel spins, is that if they are in separate orbitals by themselves, they have to be spin the same way. Yeah, Connor and then Sterling.
So all of the electron hotels are built the same. So hydrogen still, or not hydrogen's bad example, like lithium still has those other rooms,
Yes.
but the electrons don't spread out across those rooms. So it's just like once a room needs to be used, then the electrons will
Yes.
go in there.
Mm-hmm. Yep.
They won't just go in there.
And no, they always, so that's part of Aufbau's rule, is electrons always occupy the lowest energy state possible. They're not going to go to the higher rooms if the lower ones aren't filled yet. So, great question.
So this is all fine and dandy, but how is the physical way that we actually know this? Like, how is this figured out? Because this is kind of complicated.
Oh, it's way complicated.
Yeah.
Stay tuned.
Okay.
about 20 more
Because
minutes.
this sounds similar to trying to explain how dinosaurs and humans coexisted. It's like so out there to me. Hotels and stuff.
Yeah, but no, we'll get to like the experimental part of it. So, Peyton.
So
No, but
what
some
happens
people try to
when like
explain
you've got
that
one of
as
these
a
massive atoms and they're in ions? So it goes
True.
over the amount of periodic table species.
Like, what do you mean?
So say you had like your OG and it had all of the electrons filled, but it was an ion with 4 electrons.
So theoretically, there's more. As far as we know, we don't know if there's a maximum capacity to an atom. So it's just like when 119 gets made, we're gonna have an 8th energy level. And so for those, if they were able to get more and go past, they would just take up the 8th energy level. So yeah, just because it's not filled doesn't mean it's not there. So does that make sense?
Yeah.
Go to your practice problem paper for me, everybody. Max, do you have a question?
Yeah. So you said that the electrons repel each other and that's how they spin.
Yeah.
But if they're in a room on their own, how do they spin?
So you gotta remember there's a lot of electrons going, because they're still like, they're in their own orbital, but they're with other electrons in the subshell.
Okay.
Does that make sense? And that's why they have parallel spins when they're in separate orbitals, but in the same subshell. That's why they have parallel spins now. It's because they spin the same direction when they're in the same room, but on different orbitals. So, great question. Okay, go to this chart for me, everybody, and let's put the puzzle together.
No kidding, please. I'm so confused.
Okay, I'm going to go to this, but you go to that chart. Okay. Here's where the light bulb should hopefully come on for those that haven't ever learned this before. All right, so we want to write the electron configuration. That's the main objective. So let's start with the simplest thing out there, hydrogen. So that's the first one, right? So the first thing you need to do is determine how many electrons check into the hydrogen hotel.
One.
Good. So we just have one total electron. I don't want to, I'm going to squish this over. Okay. So this is like the table on your paper, right?
On the exercise.
Yes, on your practice problems.
I see.
Okay? Now, we need to figure out where this one electron goes. So we go first to Aufbau's rule, because that tells us the order to put them in. So what's the first room electrons always get put? The 1s. So in that next column where it says orbital diagram, you're going to draw one box, because 1s only is one orbital. And now for hydrogen, I only have one electron, so you're just going to put one arrow inside that box.
Does it matter if it's up or down?
It doesn't. No. As long as the next one goes opposite. Yeah. Now, for the configuration in the diagram represent the same thing. This is just visual configurations, just not as visual. So to write the configuration, you would write 1s for the room and the floor, and then you put a little 1 above the s to say, hey, there's one electron in the 1s. And that's it.
To signify if there were two.
Good. We would signify if there's two. So let's do lithium. Okay, how many electrons does lithium have? 3. Okay, notice, you always start in the first room every single time. So where's the first place we start?
1s.
Okay, so draw a box, label it 1s. Now, how many electrons can I put in that room? 2. So do 1 up, 1 down. Now, what's the next room according to the map? 2s. So draw a separate box, not connected because it's a different floor, different room. Label it as the 2s. And then now we just have 1 electron in there. So for the configuration, we would write 1s2, because there's 2 electrons in the 1s. And then right next to it, you'd write 2s1.
Would you like to put a comma in between or just?
Nope, you just connect it as a big thing.
That would be really nice.
Yeah, don't do commas. Okay, what's the next example? Carbon?
Yes.
Okay, I'm going to do it right here.
Oh, ew.
All right. How many total electrons do we have? 6. Okay. Where do we start?
1s.
Okay, so we're going to go 1s. Oh, I guess I should do the boxes first, sorry. So we have 1s. 2 electrons can fit in there. After that one gets filled, where do I go next? 2s. Put 2 electrons in there. Now, where do I go from the 2s? Good. Read left to right, right? So here was 2s. Now, that's the 2p. Now, how many bunk beds are in a p room? 3. So you need to draw 3 boxes, all connected, because that's how big the 2p room is.
Oh gosh.
How many electrons, though, am I putting in this room?
What in the world?
2, right? How do I put them in?
Okay.
Good. Separate boxes, same direction. They could go down, down, but they need to be separate boxes, same direction. Okay, so then the configuration would be 1s2, 2s2, 2p2. Notice that it's incorrect to say like 1s squared, because this is not a mathematical operation, and squaring means you're doing math, right? This is something totally different. Okay, I want you to try sodium and aluminum for 2 smiley faces. Ready, set, go.
Oh gosh.
Oh, goodness.
Try sodium and aluminum, and
That
then we'll
looks
check
much
it for
quite
some
easier.
smileys.
Aluminium?
So, your hotel is disconnected. You're a bad person.
No, it's supposed to be disconnected.
Nope.
Yeah, it is.
No.
Different levels.
No.
Look, hers is too.
Oh, I thought you disconnected those.
No. We don't.
So do you do 2P and then 3S? So, but you put the 3S after here, not with the other S.
Good, because it should be written in the order that it's filling. Yeah, do sodium and aluminum.
Beautiful. I've done it.
Oh, that's so evil.
I remember this result. I mean, last year.
Last year.
Yeah. I don't know. But I remember how much stop.
Not the complete configuration, but you didn't use it correctly. You're missing things.
Oh, really?
Yeah.
Was this
Yep, so once you get to the total number of electrons you have, then you stop filling the hotel.
What's the electron configuration? So there's 2 in it. So the L1 is 2, right? 2s1. Is that, yeah. Okay.
Wait, did we already talk about how many questions
Okay, is everyone ready to check them, or do you need 1 more minute? Photoelectron spectroscopy.
Oh yeah.
Question M?
I should do a spooky, scary Halloween smiley face.
2p6.
Yep. So you just start, always start here, and then you work your way to like this is the beginning. So
It makes
left
sense.
to right.
It just sounds like a
Fill
bunch
that
of
up with
fun.
2. So then we go 2s.
No, like, think about this in physical science. What do you mean the shape of it? It can't be like this, you know, because there's a whole different bunch of I mean, whatever, Russian. But they exist in space. They exist in spaces, so they don't necessarily orbit. And so, what the heck is going on? What?
This row would be
Oh, jeez, dude.
so then 3s will come next.
Yeah, it could.
spinning in different directions at the same time.
It's kind of the opposite. The S's start with 1, the P's start at 2, the D's start at 3, and the F's start at 3. It's just because as the atom gets bigger, there's room for more rooms. The first energy level is too small to have anything but an S. But then the second one can have an S and a P. The third one can have an SP and a P, and the fourth one can have an SP. Because you gotta imagine like our hotel is growing from like this because 3P comes before this. So it's like the third energy level for that one's not totally filled yet.
Okay, let's get them smiley faces. Come on, let's do this.
Okay, I'm just gonna say the configuration because the diagram and the configuration should
be
match, right?
the exact same.
Okay, so for sodium, ready? You should have 1s2, 2s2, 2p6, 3s1.
Wee.
That's pretty good.
Okay, for aluminum, you should have 1s2, 2s2, 2p6, 3s2, 3p1.
What
They similar.
Wait, how do people know that?
There's a 0 and it's in front of the P.
Read left, right now, right? So 3s goes to the p before the d comes into play.
Oh.
You see that, friend? Okay. All right. Skip down now to the practice problems below, everybody. Is it MN? Is that the first one we did?
But yeah, so if you were to do like the nickel or something, or no, it's like arsenic. Would you put the D before the P, or does it go S P D F G?
In how you write it or how you fill
How
it?
do you write it?
Honestly, I've seen it both ways. Some people write it where they put all the threes next to each other.
Because like right there, it's written where it goes 3.
Is that how that one's
It goes
written?
S P D F on all of them.
So like, let's see.
Up on that top right.
But then if you look at the configuration, is that what you're asking?
3 P 4. No, but do the next one. Do the next one. Like arsenic. So does the D come before the P? Yeah, the D comes before the P.
Yes, yes. For the right, because 3D comes before 4D. Yeah, so literally I write it in the order that I fill it.
Wait, so even though on like the picture, the D comes after the P, you still write out 6F.
D comes before P.
On that, but like on the picture you draw with the hotel where there's all the S's, all the D's, all the D's, all the F's.
Yes, yes.
The D comes after the P.
So the hotel doesn't show, the way it's built, doesn't show the right way to fill it. So yes. Okay, give me your eyes up here, everybody. Now, hopefully from these first few examples, you have noticed the pattern that just repeats itself. Because you're always starting at 1s, and then you always go to 2s, and then you always go to 2p. Like, that doesn't ever change. And so if you had to write the electron configuration for something like mercury that has 80 electrons,
Let's do it.
you can do it, and it's just long. But because of that, there is a abbreviated way to write configurations.
What?
So you are allowed to use the abbreviated way whenever you want. If you don't, you can use the long way, but I don't know why, unless you're just bored one Saturday.
What's the max that you would do without?
103.
Personally, like,
No, 118.
I don't know. The ones I can't, like hydrogen. But other than that, I would just always shortcut it. I mean, lithium's not much of a shortcut, but you can still use that. So the idea of the shortcut is this, everybody. So we're trying to write, so this is the next example in your practice problem. So we're doing the electron configuration for manganese, okay, which is right here.
25.
Oh, I think I know what the shortcut is.
So the way the shortcut works is, because think about this, right? The idea of an electron configuration is it tells us where these 25 electrons are located. Well, if we know that it always fills from low to high, then it's always the same pattern. So the way that you short,
the high one.
so we only write the ones kind of at the top because those are the ones that would be slightly different. So the way that you shortcut is you're going to find the noble gas that is nearest to the thing we're trying to write.
Lower above.
But it has to be lower in number. So for manganese, because noble gases are this family, so for manganese I'm going
argon.
to use
Is
argon.
Is 118 noble gas?
Technically, yes.
Okay.
Okay, so to shortcut it,
Gonium.
put AR in brackets, like so. This shortcut signifies, this symbol right here, if you don't put this, it's wrong. But by writing this letter in brackets, it tells someone else who's reading your paper, hey, 1 through 18 is already filled up. So we just now have to start at 19. So what orbital is this one right here?
Oh yes.
4s.
Okay, after 4s, where do we go?
3p.
Oh, sorry, 4s2, because there's 2 electrons in there. And then we go 3d. Now, here's another cool trick with the periodic table. You could do the math and figure out, well, how many electrons are left. But
No.
each square on the periodic table is like an individual bunk. Or an individual electron. So you literally can just count to the thing you're trying to get to. So 1, 2, 3, 4, 5. 3d5.
That's much easier.
Yes, yes it is. Okay, let's do the next one. What's the next one? Silver?
Liver.
When it's a noble gas, it's a noble gas.
Yeah. We'll talk about that though. Don't let me forget. Okay, silver is right here.
Krypton.
Right there.
So we'll shortcut with krypton this time. Okay, so then we start here, which is 5s. So we're going to go 5s2, 4d9. Once again, if we just count the d's, 1, 2, 3, 4, 5, 6, 7, 8, 9.
Wait, you say 7?
Yeah.
So you were saying that as like there's like past the F block, it's like theoretically, like there would be another level. So would that mean that there would be like another 2 rows on the periodic table theoretically?
It all depends on the big question with elements is like, when will we not be able to make any more, right? But if we are able to make more, then yes. But that is the question is, can we make more or not? So, yeah, definitely.
What do you do if the one you're looking for is a noble gas?
Great. So Peyton brought this up. So let's say I told you, hey, write the configuration for krypton.
KR.
You can't just put it in brackets.
Dang it!
I'm sorry, that's what everyone wants to do.
Brackets next to it.
But you can abbreviate with the noble gas above.
What? No.
The thing you gotta remember is this is giving us information, and writing a symbol in brackets gives no one anything. I'd have to go figure it out myself still.
But it's a noble gas, so it's gonna be all.
But remember, we're trying to see where the electrons put, and so that shows us at least where the outside ones are put, even though it is perfectly full. So, great question though, Declan. Okay, any other questions with the abbreviation method?
No, I got it.
Okay, let's have you try
Smiley.
uranium
Oh yes.
for a smiley face. So the very last one, uranium, try that one.
Oh jeez.
Is looking right.
Oh.
It's alright.
Wait, but I needed that.
Put periodic table.
I don't. Max.
Question, Jenna? Oh.
Okay. Okay, go up there.
And then we go, wait, but it's not all.
Alright, 5F. It's 5F.
Oh, here's yours too now.
Yellow paper.
check uranium?
Please.
Wave your arm if you don't want me to say the answer yet. Oh, I know some people just wave. Okay, so you should have, where's uranium? 92. Okay, so you could have shortcutted with Rn. So Rn in brackets, and then have 7s2, 5d4.
5F. I was like, wait, no, you can't do it to me.
5f1.
What if you didn't shortcut and just wrote the whole thing out?
That's fine too.
That's impressive.
1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, so on and so forth.
Yeah.
Okay, questions with configurations? Okay, so then the last thing we need to talk about today is this PES stuff. Oh wait, we gotta talk about the exceptions.
Oh no.
Go to the last page in your notes. Page, well, not the back side, but the front side of the last page. Well, page,
What does that
almost last page. Page 6. Go to page 6. So yes, if you haven't yet already, you just need to embrace that chemistry always has exceptions. And it will just always be that way. And the sooner you embrace that, the less frustrated you'll get as a student. Yes.
Oh.
So we just wrote here, everybody.
What if chemistry didn't have exceptions and we just have it all wrong? Like, what are we doing?
And then it was 5s2. Okay, so this everybody is the configuration for silver based on the rules. This is what we thought it was when we wrote before. From experimental evidence, which we'll talk about in a second, scientists have figured out that silver actually doesn't do that.
What?
Instead, silver does this.
Silver just doesn't do it.
Own hotel. What?
Silver monopolized
What?
the what?
Okay? Yes, so I would write that down on your paper.
You can't do that.
So,
Silver
with
is
this,
like
everybody,
webs.
notice something that's very important written underneath the exceptions. This little section I cut and pasted from the AP curriculum because I wanted you to understand something. With the idea of the exceptions, this is what the AP curriculum says. It says, the mere rote recall of the exception does not match the goals of the curriculum revision. You do not need to memorize the exceptions to the electron configurations. You just write a configuration as we just learned. But it does say, if it were to show you an exception, can you provide a possible reason for why the exception exists?
Nope.
So you're not expected to know the exceptions, like memorize them, but if the AP test said, hey, silver has this configuration, what's a possible reason for why that is? That's what we need to understand. So we need to understand why the exceptions happen, not memorize
Because he
them.
made his roommate angry, so he kicked him out.
Please don't write that on the AP test.
Okay.
Okay, put a star or highlight or whatever. This right here is our justification.
I can't stop.
What we have found, everyone, is that when an orbital, and I'll even add something to this, when an orbital is half filled or fully filled, it has a more stable arrangement. So if you notice between these two here,
Oh my gosh.
in this arrangement, we now have, this is half full, and this is all the way full, versus here where this one is full, but this one is neither half or full, right? It's awkward between. Half full and fully full, okay, are more stable. And so that's why the silver, literally silver as an atom, moved one of its electrons into the D to make itself more stable.
Wait, so if you were looking
How does
at
it know to do that?
the valence electrons show
It just
full,
says, hey,
but then
I'm
the one
supposed to move
inside
you,
of that,
buddy,
you've
sorry.
seen half.
Yep, it would only have one in there. This is why, everyone, the exceptions, give me your attention here, happen within those transition metals. And this is why the transition metals can have various charges, is because those electrons can get pushed around. And so sometimes iron can have 2 valence electrons, sometimes iron can have 3 valence electrons, because it can move it around. So let's look at another one. So chromium's real configuration would be this. So chromium, so Ar, 4s1, 3d5. So this is what it really is, rather than what we would think, like so. So this is the real, what it is. Does everyone see what that does for it?
Yeah, half and half.
Yeah, so now it has 2 half-filled orbitals. One before it had 1 full and the in-between.
So it seems to always do it with S.
So there's always 6.
Like, is there any other exceptions?
It really always falls within B. It's because that S, it's just like we talked about, right? That 4s, or any S, and the D are so close to each other in that overlap. And so it's fairly easy for the atom to move the electron around. It's not going to move it from a big jump, right? You can't, like, on its own, it can't just move it from an S all the way to a P. It's too big of a jump. So, great point, Karen. Yeah?
So, like,
Unless you shoot.
I know it makes it more stable, but like, how does the atom move it there? Like, what makes it move there? What makes it?
So it uses just some energy to jump the electron up.
But how does the atom be like, hey, we need to move this? The atom can't think.
It's just where it wants to be.
It just, we'll just think of energy, right? That things always go to the natural state of lowest energy. And for that electron to be there is lower in energy than it for it to be at the other place. Right? Because that's just like basic, like how physics works, right? That things always flow from high to low energy. So, yeah, great point though, because it does sound weird to think like silver made that conscious decision to do that. No. Okay, last thing here, everybody. We mentioned this last time about this idea of photoelectron spectroscopy.
Oh.
Oh, yeah. Oh, yeah. The thing that shoots the electrons.
Yes. Okay. So the idea of this,
I was
everyone,
just talking about that.
is with photoelectron spectroscopy, we can take a sample, and if we send energy into it, and that energy has enough. Sorry. Let me back up. So we have our sample. And then we send a wave into it. If that wave has enough energy, it can cause changes within the atom. For example, if that light that is coming in has the energy of an X-ray, which X-rays are pretty high in energy. Well, there's a lot of different types of X-rays, right? But if it has enough energy, it can literally kick off an electron from the atom, from the sample. And if you use enough energy, you can strip all the electrons away.
Oh, poor atom.
So you can take an atom and you can rip off all its electrons.
Keeping their kids out of the house when they get too old.
Just put that on a laser pointer and
Does
just.
it like just like fall apart?
It falls apart and is plasma. Like that's what plasma is.
Lightning.
It's plasma is we have ripped away, like plasma is, yeah.
So
Plasma's weird, I can't talk too much about it. But Russell.
Plasma is
So,
painful.
Is it the wave or the
Well,
lightning?
yeah, but isn't stuff the
It's in your bones, not your blood.
They wouldn't have enough energy.
Wow. It's gross.
Plasma would cause other changes.
Yes, I thought you would go in class.
Wasn't that one of the?
Yeah, so what this does, so let me show you this and this might answer what you're asking. So from this, everyone, visualize with me here.
And then part separate it.
Okay, focus back, focus back. So we shoot the X-rays at the sample. The X-ray goes in, electrons come flying off. We determine, like the scientist who does it, can determine the energy that's put in. If we know the energy that goes in, they're able to measure the energy that comes out, and from that we get these diagrams. Okay, what this diagram shows is it shows the different number of electrons. So notice your axes here. So the y-axis is the number of electrons. So for this particular sample, we had 1 electron that came off with the energy of 0.52. We had 2 electrons that came off with the energy of 6.26. And you have as many peaks as you do electrons. This actually proves the existence of the different subshells and levels. So for example, this particular sample, maybe write this off to the side of that picture in your notes. This is for lithium. Okay, so we were analyzing a sample of lithium. With lithium, we know from the periodic table that lithium has 2 electrons in the 1s, 1s2, and it has 1 electron in the 2s. Right, that's its configuration. So first off, you need to notice something important because sometimes it does it in 2 directions.
Oh.
The lower the energy, means the farther away those electrons were from the nucleus.
And isn't that one also low because it's like all by itself? So it kind of wants to get rid of it.
Good, and that's why it's so low, especially for lithium, because lithium's actually totally fine giving up its first electron. Yeah, very good. So the lower the binding energy, the farther away from the nucleus those electrons are. So then, yeah, it's like our valence ones, and then as we go in, those are the core. So if we were to label these peaks based on our configuration, this peak would correspond, thank you, to the 2s electron, because it was low in energy. And this one would correspond to the 1s. So take a look at your practice problems here. Now let's look at one where we don't know what it is and try to figure it out.
Will the electrons go back to the atom once the signal is removed, or are they just left?
Not until they like put them back, because they go into like a detector and stuff. So it's not like. But that's how then you could like change your plasma like that.
Okay, so once you make a plasma,
So you can turn plasma into like.
Yeah.
You can turn plasma into lithium.
I don't understand fully how it works, but yes. Yes.
So, with all this electron and orbital stuff, what the heck is going on with magnets? Because those are like free moving electrons and also like conducting electricity and like power and taking that. And like, what's going on there with all these orbitals?
So we'll have a unit, it's not for a while,
Oh.
but we'll talk about electrochemistry and like the flow of electrons.
Oh boy.
Which hopefully will answer that.
Okay, we'll do.
Okay, last thing here, everybody, and there will be one of these questions on the test, looking at something very similar to this, okay? So now, there's a difference between this graph slightly and the one we just looked at. Does anyone see the difference?
I do. It has more peaks.
There are more
reversed.
peaks. The energy is the other way around. Now, I'm
Oh.
showing you both because I've seen it both ways, and so I don't know which way they're going to show it. But just pay attention to what does it mean if it has high energy or low energy? Like which?
High energy is closer to the nucleus.
Good, so high energy is closer to the nucleus, so in this case, my valence electrons would be over here. Good, low is valence, high is inner. So I'm going to start inner because I don't know where I'm ending. So what's the first orbital that always gets filled?
1s.
Good. So this peak must mean 2 electrons in the 1s. What comes next?
2s.
Good, so this peak would be the 2s. The one next to it would be,
2p.
why is that one so tall?
Because it has 6 electrons.
Because there's 6 electrons in the 2p. Okay, now this one would be, and this last one then must be 3p.
Wait, so even though there's 6 electrons in the 2p, it has less. It takes less energy to get rid of all 6 of those electrons than the 2s. Like, is it saying that there's less?
Yes.
So even though there's 6 electrons, it takes less energy
To remove them then from the 2s. Okay, now everybody, first off, look at the periodic table. If you go to the 3p row, we should be able to cross off, okay, I know it's not boron, because boron would stop at 2p.
It's also got sodium.
Good, I can also cross off sodium, because sodium would need to go to 3s. But now I'm between two of them that are both on the 3p. Haley, were you gonna ask your question, or did you have a thought?
With the highest energy, it will all take 1s.
Good. Yep, the height, because that's the innermost one. Yeah, good connection. So any thoughts of how I distinguish which one it
There's
is?
only one electron in 3p.
Look at the size now. So notice that it's half the size of the S.
Oh, shoot.
So if there's 2 electrons in that, then that means there's only 1 electron in the P, which means it must be aluminum. Questions on PES diagrams?